Good afternoon. So far, we discussed about linear functions, quadratic functions, and polynomial functions, also rational function. Today, we will discuss regarding some another kind of function called exponential function. Exponential functions, they are used, we use exponential function to model any process where the growth rate is very high. Exponential function represent the process where the function grows very fast. For example, let us look at this graph. Let us look at this graph. I have graph of three function. The red one, this is the graph of f of x equal to x. This is a linear function, and this is the graph of f of x equal to x to the third, a polynomial function, cubic function, and this is the graph of another function f of x equals 3 raised to the x. We can notice that let us say for x equal to, for example, here for x equal to, let us say, I think this is x equal to 1. For example, for when x equal to 0.5, the cubic function is only up to this, the linear function is a little bit tall. However, the exponential function is very tall. Well, we can notice this characteristic if in fact if we take better, if we take even larger value for x. For example, if we zoom out and take x equal to, for example, 2, the linear function is only up to here. The cubic function is little bigger than the linear function. However, the exponential function, the third function, grows so big. So this is the graph of one exponential function, and it shows how fast the function grows. So when we think about fast growing process, one of the example of the fast growing process will be the credit card loan we take. If we do not pay the loan of the credit card because of the way bank charges us interest, the loan amount grows exponentially very fast. Well, let us look at exponential function now. A function of the form f of x equal to a number raised to the x, b raised to the x. If the variable x is in the exponent, b is just a number and x is the exponent. If the variable is in the exponent, we call it an exponential function. Well, we want b to be positive, and we don't want b equal to 1. So b should not be equal to 1. If b is 1, 1 to the x is 1, so it is not an exponential growth, it is not an exponential function. Well, let us look at few examples of exponential function. For example, let us say 5 to the x. If we want to graph 5 to the x, we can make a table. Let us say x and y, x and f of x. For example, we can choose x equal to -1, that means 5 raised to the -1, which is 1/5, and if we choose x equal to 0, that is 5 raised to the 0, which is 1, and if we choose x equal to 1, we will get 5 raised to the 1, which is 5, and if we take x equal to 2, it is 5 raised to the 2, so 25. If we take x equal to 3, it will be 5 raised to the 3 and 125. So if we want to graph it, For example, at -1, the function is 1/5 here, at 0 the function is 5 somewhere here. So, this is 5, 1, the function is, let me erase this. So, the function is 1 when x equal to 0. So, this is 1. When x equal to 1, the function is 5, it reaches here. If x equal to 2, suddenly it goes so far up. So far up, I do not even have a space here. So, the graph will look like this, very fast growing process. Well, not only the fast growing process, but also the fast decreasing process, not only the fast increasing process, but fast decreasing process can also be modeled by exponential function. For example, let us look at f of x equal to 1/2 raised to the x. So, let us try graphing it as before. So, if we try graphing it as before, let us say f of x, f of x and x, let us make the table like before. If x equal to, for example, -1, we get 1/2 to the -1. 1/2 to the -1 is reciprocal of 1/2, which is 2. If we take x equal to 0, 1/2 to the 0 is 1. If we take x equal to 1, we get 1/2. If we take x equal to 2, for example, we get 1/2 square, which is 1/4. So, if we want to graph it, so let us start from -1, here is 0, here is 1, here is 2, for example. So, at x equal to -1, the function was 2. So, we will have a point here, this is 2, let us say, and here is 1. When x equal to 0, the function is 1. So, we have a point here. X equal to 1, it is 1/2, so it will be here. X equal to 2, it is 1/4, so it will go down. So, look at this curve decreases very fast. It is almost collapsing towards the x axis. So, the fast growing or fast increasing process can be modeled using exponential function. One note, let us remember this x square, this is polynomial function. If the base is the variable and the exponent is a integer, that gives us a polynomial function. However, if base is a number and the exponent is the variable, exponential function means we need a variable x in the exponent. So, let us identify the difference between x square and 2 to the x. X square is a polynomial, however, 2 to the x is exponential function. Some characteristic of exponential function. The domain of exponential function is everything from -infinity to infinity. Y-intercept is always 1, because if we think of the function f of x equal to b to the x, in order to get y-intercept, we should replace x by 0. If I replace x by 0, I will get b to the 0, which is 1. So, y-intercept is 1, and as we have already seen few graphs, the graph of the exponential function goes like this. It will never intersect x axis. So, exponential function will not have any x intercept. The basic exponential function will not have, the basic exponential function b to the x will not have any x intercept. Now, if the number b is bigger than 1, like 5 in the previous example, the exponential function grows like this. However, if the number b is less than 1, like 1/2 in the previous example, the exponential function behaves like this, it goes decreasing. B bigger than 1, exponentially increasing. B smaller than 1, like 0.5, 0.75, 0.1, 0.2, it is decreasing. And you can notice the graph of the exponential function tries collapsing to x-axis. So, we say x-axis is the horizontal asymptote for exponential function. Well, several exponential function can be graphed using the notion of transformation. So, if we want to graph let us say 2 to the x minus 1, by knowing the graph of 2 to the x, well, the graph of 2 to the x will look something like this. Remember, it has to go through 1, okay, and 2 to the x means the number 2 is bigger than 1, so it is increasing exponential function. Now, this is f of x equal to 2 to the x. If I want to graph 2 to the x minus 1, recall that subtracting a number from a function implies the vertical translation by down by that unit. So, right now I am looking at vertical translation of this function by 1 unit. So, this graph, entire graph will go 1 unit below. So, we will see a graph of this type. So, this is the graph of f of x equal to 2 to the x minus 1. Well, better to see this characteristic using this graphing calculator. Let me erase whatever I had from the previous work, and let us see the graph of 2 to the x and 2 to the x minus 1 together to notice how the graph translate by subtracting a number from the function. So, we have 2 to the x minus 1 and 2 to the x graph together. Let us see. So, the red one, this is the graph of f of x equal to 2 to the x, and this is the graph of f of x equal to 2 to the x minus 1. The red one is going down by 1 unit. Okay.